Hi, my name is Jordan Quan, and this is my grade 12 Advanced Functions CCT. I am going to walk you through a question from Unit 2, Polynomial Functions in the Nelson Grade 12 Advanced Functions textbook. Before we start, we are going to go over some of the basics of polynomial functions, which we will need to successfully solve the problem. First off, what exactly is a polynomial function? Well, a polynomial function is a function involving only non-negative integer powers of x. This involves functions such as the quadratic function and the cubic function. Next, I'm going to define some terms we will need to know. Here's an example of a polynomial function in factored form, which we are going to use to help define these terms. In this video, we are only going to be using polynomial functions in factored form, because in order to graph a polynomial function or write the equation based on a graph, the function must be in factored form, as it gives us the zeros, or in other words, the x-intercepts. The first term we will define is the degree of the function, which in factored form is the sum of all the powers. As you can see in the example above, one of the factors have a power of 2 and the other has a power of 1. So this example is a third degree function. The order is the power of each factor, so the factor x minus 3 is of order 2 and the factor x plus 1 is of order 1. Lastly, the 2 in front of the function is called the leading coefficient and is also known as the a value. This value adds a vertical stretch or compression, and the sign of this value determines which direction the function opens. Another important term we need to know to solve this problem is called end behaviors. This is the behavior of the graph as x approaches infinity and negative infinity. Let's start by looking at the quadratic function in its most basic form. Stating the end behaviors of a function is always written in the format as x approaches infinity, y approaches blank, and as x approaches negative infinity, y approaches blank. As you can see, in this case, as x increases or approaches infinity, y also increases, so y approaches infinity. And as x decreases or approaches negative infinity, y still increases, so y approaches infinity. Therefore, the end behaviors for this function are as x approaches infinity, y approaches infinity, and as x approaches negative infinity, y approaches infinity. If you look at the equation of this function, you can see that this is a second degree function, because the sum of all the powers is 2. And since the degree is 2, this is an example of an even degree function. You'll see why this is important after we look at a few more examples. For this next example, we're going to look at a cubic function. As x approaches infinity, y gets bigger, so y approaches infinity as well. And as x approaches negative infinity, y gets smaller, so y approaches negative infinity. And because the degree of this function is 3, this is a third degree function, therefore is an odd degree function. The reason that even and odd degree functions are so important is because there's a pattern in their end behaviors. As you can see here, this is an odd degree function, and the ends of this function go in different directions. If we rewind, we can see that in this even degree function, the ends point in the same direction. This pattern applies to any even or odd degree function. For example, 4th, 6th, and 8th degree functions will all have end behaviors going the same direction, and 3rd, 5th, and 7th degree functions will go in different directions. As I mentioned before, the sign of the leading coefficient also impacts the end behaviors. When the sign of the leading coefficient changes, it flips the whole function over the x-axis, therefore flipping the end behaviors as well. Great, so we discussed what happens at the ends of polynomial functions. Now let's go over what happens in the middle. We do this by looking at the order of the function. Here is another polynomial function to help illustrate this concept. If you take a look at the zeros of this function, which is where the function crosses the x-axis, you can see that each zero has a different action. This is due to the different orders. The 0 at negative 2 is of order 1 and the function passes through the point. The 0 at 2 is of order 2 and the function bounces off the point. And the 0 at 4 is of order 3 and it swerves through the point, which we call cubic action. Just like end behaviors, there's a pattern for the order as well. If the order is 1, the function goes through the 0. If the order is even, it bounces. And if the order is odd, it has cubic action. Awesome! That's all the knowledge on polynomial functions needed to finally tackle this problem. This question can be found on page 148 and is number 11. The question states, a company's profits and losses during a 15-year period are shown in the table. A. Sketch a graph of the data using years since 1990 as the values of the independent variable. B. If x represents the number of years since 1990, with 1990 being year 0, write the polynomial equation that models the data. C. Is this trend likely to continue? What restrictions should be placed on the domain of the function so that it is realistic? Clearly, this question is from Unit 2, Polynomial Functions, as in Part B, it asks us to find the polynomial equation that models the data. This question is asking us to sketch a graph of the data with the year since 1990 as our independent variable. As you know, the independent variable goes on the x-axis. We are graphing a 14-year span, so we can label our x-axis starting at 0, with 0 being 1990, and go up by 2s until we hit 14. For our dependent variable, the profit or loss in thousands of dollars ranges from negative 216 to 120. So a good sized scale would be to label up to 300 in each direction, with 100 being the interval. Now, we just have to plot the data. Sweet, that's all we have to do for part A. Let's move on to part B. B is asking us to write the polynomial equation that models the data. The steps to do this are, look at the end behaviors to determine if the function is even or odd, then look to see where the zeros are located and what action they each display to find their order, and lastly, solve for the a value. First, when we look at the end behaviors, we see that as x approaches infinity, y approaches infinity, and as x approaches negative infinity, y approaches negative infinity. Therefore, since the ends are going in different directions, we know that this is an odd function and will have an odd degree. Next, if we look at the zeros, we can see that they are at x equals to 2, 9, and 12. And because the function goes through all of these points, all the factors in our equation are going to be of order 1. Now that we know all of these properties, we can fill into the equation what we know. So the equation will look like f of x equals a times x minus 2 times x minus 9 times x minus 12. We can confirm that this makes sense because the degree of this equation is 3, which means it's an odd function, therefore following the end behaviors of the graph. To complete the equation, all we have to do now is to determine the a value. To do this, we need to take a point from our graph to plug into our equation, and just isolate for the a value. I'm going to use the point 750. 50 is our y value, and we need to replace all the x's in our equation with 7s. Then just simplify and isolate for a. Nice, our a value is 1. We're done! Just kidding, we can't finish this question without checking our work. To check our work, we just take another point and plug in the x value into our new equation. If we get the corresponding y value, our equation is correct. This is because this means that our equation matches our graph, therefore correctly modeling the data. This time, I'm going to use the point 480. When we plug in 4, we get f at 4 equals 80, which is the y value of the point we plugged in. This confirms that our equation is correct. Because this is a word problem, we need to answer in a sentence. Therefore, the polynomial equation that models this data is f at x equals x minus 2 times x minus 9 times x minus 12. That's the end of part B. Finally, on to part C. This question asks, is this trend likely to continue? What restrictions should be placed on the domain of the function so that it is realistic? Looking back at our graph, we can see that the trend of this graph is as x approaches infinity, y approaches infinity. This means, in the context of this question, that as the years progress, the company's profits would keep on increasing forever. If this was the case, I would invest some stocks ASAP, but in reality, this trend is not very likely to continue. So, to answer the question, no, because the end behaviors of this function state as x approaches infinity, y approaches infinity, and this means that the company's profit would increase forever, which is not likely at all. Restrictions that should be placed on the domain of this function are x must be greater than 0 and less than 14. X can equal anything after that. This means that this function only models the data from 1990 to 2004, which restricts the profits from increasing forever, therefore making this function realistic. Before I end this video, I want to talk about some real-life applications of polynomial functions. Polynomial functions are used in many different ways in the real world. Firstly, as seen in the question we just solved, in economics, polynomial functions are used to do cost analysis. Engineers also use polynomials to describe curves in structures such as bridges and roller coasters. Polynomial functions are even used in meteorology to create mathematical models to represent weather patterns, which are then analyzed to make weather predictions. As you can see, polynomial functions have many different applications in the real world.